So in our first video on properties of the determinant, we established some important properties for elementary matrices. Let's see if we can recap. We might refer to these today. We said if E, remember we had three types of elementary matrices. We'll just call E a generic one. If E is an elementary matrix, then the determinant of E, you had three possibilities, right? It could have been -1 if you had a permutation elementary matrix. It could have been R if you had a scaling elementary matrix. Or it could have been simply 1 if you had a replacement elementary matrix. And this is with R not 0. Anytime you're doing a scaling elementary matrix, the R value is not 0. So what's important here is that when you take the determinant of a elementary matrix, you take the determinant of an elementary matrix, it's never 0, right? It's either -1, R that's not 0, or 1. So also recall another thing, another important property for determinants of elementary matrices that we looked at in the first video. So let's say you have an elementary matrix E. If E is an elementary matrix, that's n by n. Come on. And A is also n by n. And A is n by n. Then when you take the determinant of E times A, so if you're multiplying on the left by E times A, so E first and then A, you can split apart the determinant. This is called multiplicative. The determinant is multiplicative when you have an elementary matrix times another square matrix. So two important points there. So I want to remind us of those because we may use them later. So the big result today that we're going to look into is a theorem having to do with determinants of elementary matrices. This is a very important result. And I'm going to call this determinants of invertible matrices. Determinants of invertible matrices. So let me write the statement. An n by n matrix, let's call it capital A, is invertible if and only if the determinant of A is not 0. So a matrix being invertible is equivalent to saying it has a non-zero determinant. That's the same statement as saying a matrix is singular if it has a determinant of 0. So a matrix would be singular precisely when it has a determinant of 0. It's invertible when it has a determinant that's not 0. So we actually saw this happen when we were looking at 2 by 2 matrices and the inverse of a 2 by 2 matrix. But we want to prove this in general for an n by n matrix, a square matrix of any size. We have the tools to prove it. Let's go ahead and see if we can. Proof. Before I get proving the two directions of the if and only if statement, I'm going to set up some preliminaries. So first I'm going to say let A, be an n by n matrix. Be nice if this actually worked. This pad is really getting on my nerves. Let A be an n by n matrix such that A is row equivalent, that squiggly line means row equivalent to R, with R, so R is a matrix, it's the reduced row echelon form, RREF of A. So imagine you take A and you reduce it completely to reduced row echelon form. So that means if you can reduce A to reduced row echelon form, that means there's a sequence of elementary matrices. Then there is a sequence of elementary matrices. Right, these are the matrices that perform the row operations on A when you multiply from the left. There's a sequence of elementary matrices, say E1, E2, and so on, all the way up to how many there are, we don't know, we'll just say EK, such that I'm going to take E1 and operate it on A, E2, and operate it on E1 times EA, and you keep going all the way to EK is going to operate on all the previous matrices that are operating on A. And that's going to give us R, right? So E1 does a row operation on A. E2 does a row operation on that matrix. E3 will do a row operation on that matrix, all the way to EK, which does a row operation on the matrix. And we get R, right? That's the reduced echelon form. Okay, so now I'm ready to start up my two-directional proof. I'm going to start by assuming first that A is invertible. I'm going to try to get to the determinant of A is not 0. So we're going to do the forward direction of the proof. So here we're going to suppose A is invertible. Now remember, if A is invertible, that means it's row equivalent to the identity, right? And that's from the invertible matrix theorem. That was one of the parts. We actually proved it before the invertible matrix theorem, but that was one of the equivalent statements of the invertible matrix theorem. A is invertible if and only if it's row equivalent to the identity. So that means then this R right here is the identity in this case. Then R, the reduced row echelon form of A, is the identity. Right? So what does that mean? That means EK, E2, E1, A is the identity. So here we're just replacing this R, the identity. Now I'm going to take that equation we just wrote there, EK, E2, E1A equals identity. We're going to take the determinant of both sides. So we have, let's take the determinant of both sides. Okay, so I have the determinant of the left side. I'm going to take the determinant of the right-hand side, the determinant of the identity. Now, we're going to use the multiplicative property of the determinant when you have a elementary matrix on the left. So basically, you can break this apart. We have the determinant of EK, because that EK is on the left, and then you're going to have like an EK minus 1, and so on and so forth, all the way. Determinant of E2, you can peel off that determinant E2 from the left. You can use that multiplicative property, determinant of E1, determinant of A, and that's all going to be equal to, remember we said that the determinant of the identity is 1, right? Why is the determinant of the identity 1? Well, the identity is a triangular matrix. It's both upper and lower triangular matrix, the identity. We said the determinant of a triangular matrix, either upper or lower, is the product of product of its diagonals, well, the identity has just ones down the descending diagonal. So you just take 1 times 1 times 1 times 1. So the determinant of the identity is 1. All right, good. Now also remember that we said that the determinant of elementary matrices are either 1, R, or -1. -1, R, or 1. And they're non-zero, right? Elementary matrices have determinants that are not 0. So what we can do, we can divide both sides by each of these determinants for the elementary matrices. So basically, I'm going to divide both sides by the determinant of EK, EK minus 1, EK minus 2, all the way through determinant of E2, through the determinant of E1, and we're going to have left, determinant of A will be left on the left side. On the right side, we're going to have 1 over determinant of E1, determinant of E2, and so on and so forth, determinant of EK. Right, these guys are not 0. Remember, determinants of elementary matrices are not 0. So you have 1 divided by some number, right? None of those determinants could be 0. So this means this is not equal to 0. The determinant is not equal to 0 here. So that's one direction of the proof. We've proved that if A is invertible, the determinant is not equal to 0. Okay? So the next thing we want to do, we want to prove that if the determinant is not 0, then A is invertible. Let's see if we can do that. Let's go green. Come on. It's not working. So we will show if now the determinant of A is not 0, then A is invertible. So that's the reverse direction we want to show. It turns out it's not super easy to do this directly. So what we can do, we can prove the contrapositive of this statement, which is logically equivalent. So the contrapositive of this statement, let's write that down. The contrapositive, we're going to say it suffices to show the contrapositive. The contrapositive is logically equivalent, contrapositive. That is, if what? You negate A is invertible, so you say if A is singular, then you negate the determinant of A is not 0. That would be, the negation of that would be the determinant of A is 0. So what we're going to do, we're going to actually prove the contrapositive of that green statement, which is if A is singular, then determinant of A is equal to 0, equal to 0. Yep. Equal to 0. So let's see if we can do that. Let's scroll a little. Going in yellow. Suppose, here we're going to suppose A is singular. Suppose A is not invertible, right? A is singular, it's not invertible. Now back in the preliminaries, we had some blue writing, right? We said that A row reduced to R, where R is the RREF form of A. So if you think about what that means, if A is singular, then, well, then R, the RREF version of A, the reduced row echelon form of A, is not the identity. And remember, A is invertible if and only if it has n pivots. So if it's not invertible, if it's singular, then it has to have less than n pivots. So R is not the identity, and R has fewer than n pivots. So R is an n by n matrix, and it has fewer than n pivots. So what does that mean about R? So that means there's going to be a row. Actually, the bottom row will just be a row of zeros, right? It's going to be missing a pivot in that bottom row. So thus, R, the reduced row echelon form of A, has a bottom row of zeros. Bottom row of zeros. Just all zeros. It's because there's no pivot. All right. Now, let's remember, back when we were doing our preliminaries, we had that equation where you had your elementary matrices times A convert into R, right? They transform A into R. So we're going to use that equation. We're going to take the determinant of both sides. So I'm going to take the determinant of EK, dot, 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 E2, E1, A, and then the determinant of the right-hand side, determinant of R. Again, R is the reduced row echelon form of A. So using the properties of the determinant, remember, determinant is multiplicative when you have an elementary matrix multiplied on the left of another matrix. So we can basically pull these determinants apart on the left. You have determinant of EK and so on and so forth. Determinant of E2, determinant of E1, determinant of A. And the big question is, what is the determinant of R? Well, think about what R is. R is an R is a row-reduced matrix. R is a row-reduced matrix with zeros in the bottom row. So what you could do, you could expand across that bottom row, and if you expand across that bottom row with all zeros, it's going to have a determinant of 0. And then from there, what we can do, we can divide both sides of the equation by determinant of EK, determinant of EK minus 1, determinant of EK minus 2, all the way down, determinant of E2, determinant of E1, right? Because those guys are non-zero. Determinants of elementary matrices are non-zero, so we have what? Determinant of A equals 0 divided by determinant of E1, determinant of E2, so on and so forth. Hold up, those are not L dots. Those should be C dots, right? C dots. Get it right. Determinant of EK. And that's just going to be 0. All right. Determinant of A is going to be 0 divided by any non-zero number, 0. And that's the end of the proof. All right, we wanted to prove that if A was singular, then determinant of A is 0. So that proves the entire statement of matrices are invertible if and only if they have non-zero determinants.